I'm Anthony Daughtry. Just for due diligence, this work was done when I worked for Solidigm, which was Intel's NAND division that was purchased by SK Hynix. I do not currently work for them, just so that there's no confusion. And Kurt Bruns was my partner in this. He's not here. He did the coding, I did the architecting. Okay, I'm currently with a company called Index Exchange. Everybody buy a copy of my book if you haven't already, etc. One thing about some characteristics of Ceph RGW deployments. They can have a wide variety of object sizes, which really impacts how we architect them for cost and performance. The workload is very often read mostly, sometimes overwhelmingly so, with drive writes as little as 0.01 drive writes per day. That's a figure from a production multi-tenant object service that I can't name. Large objects demand high read throughput and don't cache well. Small object operations have more overhead per gigabyte and are served well by fast storage with low latency. So this gives us some dilemmas. We have mixed workloads with conflicting demands. Spinning hard drives are a traditional choice for an attractive dollars per terabyte on just the drive itself. But as hard drive capacities are increased, I think, can you order 22 terabytes today? If you can't, it'll be real soon. But still the same legacy interfaces. So more and more behind the same interface, and that's so much a bottleneck. And with hard drives, seek latency can be a real problem as well, moving the heads around. Ultra-dense servers are very popular with object storage. 9800 drives, in a 4U spinner, top loaders. Just when you look at that, seems like it minimizes CapEx, but there's more to the picture than that. The underlying storages are prone to hotspots. This is something that I never really saw in RBD so much, but with object storage, there would be people hitting the same, reading or updating the same object multiple times per second. And that got to be a real problem with hard drives. And the small object operations could really saturate the IOPS. And you can play some games, like dynamically adjusting the scrub sleep, etc. But at the end of the day, there's only so much you're going to get out of a spinner. Conventional wisdom is that SSDs are awesome, but they aren't dense enough and they're too expensive, right? No, not necessarily. I'm not sure if I have it later in here, but the SNIA has a TCO calculator, which is fantastic. It lets you put in not only your drive costs, but data center RU costs, OpEx costs for how much does it cost you to actually change a drive, get somebody on site to do that, the racks themselves, the power, et cetera. And when you plug in all of those numbers, you can be very surprised at what your actual TCO is. Not just the cost of the drive, but the cost of the drive bay. And so one way that Ceph can address this is by mixing media. One of Ceph's strengths is the ability to provision multiple storage pools with varying uses, durability, availability, on different kinds of underlying storage drives. With RBD for block, this is really straightforward. You provision and select an erasure-coded hard drive pool for cold data, a replicated SSD pool for hot data, etc. For RGW, the S3 protocol specifies a storage class that are a natural fit for object storage. And that's, it can be specified in the header in the RGW request. So you could have, for example, a cheap and deep but slower object class for huge objects, and a more expensive but faster storage class for small objects, and size those, based on your workload, so you don't have to buy, all Optane for, storing your pirated movies dubbed into Portuguese, which, again, I don't make stuff up. This is something I've seen. And so the S3 RGW user can specify a non-default storage class per bucket or per object, but getting compliance, especially if the customers are paying customers, they're not your internal colleagues, can be very difficult. Compliance is difficult to enforce, especially in multi-tenant environments. If they're paying you money, the product people may not even let you ask them to comply with this. They want you to just do it all transparently, especially if your company's hallmark is simplicity. The last thing you want to do is start making things as complex as AWS. And Ceph allocates at least the min alloc size option of underlying storage. Current default is 4 KB. That has varied a bit over time for hard drives and SSDs. You can go back and look at the Git history. And so if you're writing a 1 KB Ceph object, you're going to use 4 KB of underlying storage. Mark Nelson has a fantastic spreadsheet you can find online that shows you the visualization of that wasted storage. So SSDs technologically benefit from aligning the min alloc size to their internal indirection unit, kind of the block size at the flash layer, FTL, the flash transition layer in the drive. But tiny S3 objects, thus constrain drive capacity, where, if you're allocating, as much as 64 KB with, you're wasting a lot of storage, especially when you factor in replication. The latest QLC drives are attractive hard drive alternatives with faster writes than hard drives, reads that are very competitive with TLC SSDs, but at lower cost, and density as high as 1 petabyte per rack unit. Actually, you could do 1.5 petabytes per rack unit of raw space if you tried hard enough. You can get a 30 terabyte QLC SSD in a E1.L form factor, and somebody makes a chassis with like 100 or something of those. And soon Solidigm is going to come out with a 60 terabyte QLC drive. So rack units cost money. Who's ever not been able to expand because you didn't have any rack space? Yep. So one thing about QLC is, in order to give it a price advantage over TLC SSDs, is that sometimes that indirection unit, the block size, can be as high as 64 KB. Sometimes it's 16, we might see 8, but not just the 4 KB that a lot of things assume. And so for maximizing performance and endurance on those SSDs, especially since QLC doesn't have usually as high of endurance as traditional TLC, you really want to align min alloc size with that IU size on the drive. That helps with, it helps the drive performance and, the drive endurance. But then, looking back at how Ceph allocates, if you're storing small objects, that makes the, min alloc size decrease was all about getting rid of the space amplification. And here, to use this new media, we have to put it back up, and so the space allocation becomes a problem. Especially when EC is used, classic space amplification, and so it's kind of a dilemma. And so if you can pack your objects together into larger objects, that helps solves it. But when you have a mixed workload, you can have mixed backing stores. And so that was the idea here. Space amp and replication. This just kind of shows how the min allocation space amp can be a problem. In an extreme case, 4,700% total rate amplification. That's not good for anybody. If it's a very small percentage of your workload, you just eat it and live with it. But if it's a significant fraction of your workload, then that's a significant problem. Okay, and here's some details on testing. Showing how the space amplification and write amplification go. And these details are in the slides. I can send the deck to anybody who wants them. And I believe these are also available online as well. These sample scripting. I won't spend too much on the time on the details here. And so how do we solve the problem of having RGW have multiple storage classes backed with multiple different kinds of pools for different media or different EC versus replication, et cetera, without having to rely on user compliance? And I talked to the RGW folks about this at length, and the by far the easiest way was to use Lua, which I think Lua scripts came out in Pacific. And Pacific gives us the ability to tie Lua scripts to various RGW events. And in this case, we care mostly about the objects coming in, being uploaded. And so we can use Lua hooks to direct S3 objects at upload time without or even overriding a user-supplied storage class. Now, this is all opt-in. I would not dream about changing default behavior, principle of least astonishment, right? And so, for example, the default storage class might map to a normal 3-replicated TLC SSD pool with a 4KB min alloc size traditional SSD pool, which is terrific for small S3 objects, fast metadata operations. But a lot of time, with object storage, the use cases don't care so much about latency. They care more about throughput, and they can handle, some more slowness, especially if they're read-oriented. And so we might also have a bulk storage class that can be configured to map to capacious, say, a QLC SSD pool, notably the Intel Solidigm P5316 QLC, which you can get in 15 or 30 terabytes, and that has the 64 KIU. And so that would let you get, huge reads at, at better density and less, capex than TLC, and dramatically better than hard drives. And QLC can offer the best of both worlds. You get NVMe performance because, they're all, at least in the Intel Solidigm product line, they're all NVMe. And the reads are very, very competitive with TLC, and the writes are still faster than hard drives. And TCO is, surprisingly competitive with hard drives. Some things will say, in a couple years we'll cross that. When you use the SNIA calculator, you may well have already crossed it. If you spend a lot of your time dealing with hard drives causing incidents, what's the cost of that degrading your service? QLC writes and endurance are slower and lower than TLC, but remember, in an object service, you might need only 0.01 drive writes per day of actual endurance over 5-7 years, something like that. And again, that's real life. It's a fact. SSDs rarely run out of endurance. 99% of SSDs never use more than 15% of their endurance. Now, the figure may include desktop client drives, but it's still true that most SSD failures are firmware. Few people ever run out of endurance. And so a drive with 0.43 drive writes per day rated endurance may still be plenty more than you need. So endurance is the last thing that would be a gating factor. TLC SSDs, conventional enterprise SSDs, offer faster writes than 4K blocks. They minimize the space amp. And so you can use those for only the data that has those characteristics. Or you can put a varnish cache in for your reads on your small objects, for the to get rid of the hot spotting, etc., so that you use Optane if you can still get them. With the Quincy release, we can enable server-side Lua scripts to rewrite the storage class header when S3 objects are uploaded. There are plenty of other criteria that you could use. This was all driven about enabling QLC, but you could use it for all kinds of other media, greater or lesser replication, et cetera, whatever you need. And so in a Quincy example, we can steer S3 objects by size. And for example, assuming that a multi-part object are always going to be large. But many other strategies can be realized. When we were doing this work, Sage asked us to automatically detect the automatic min alloc size for an OSD. And the min alloc size in an OSD is baked in when you create it. You can't change it after the fact. And so if you're going to use, say, novel QLC with a large IU size, in order for it to work well, you need to create that. And so in newer kernels, it turns out they give you an optimal IO size. And so our work also gives you an opt-in ability to have OSD creation automatically set the min-alloc size to match what the device tells you. And again, principle of least astonishment, you have to opt into that. And so here's the excerpt from the options list within Ceph. Use the kernel optimal I/O size, false by default. And here's an example of sysblock NVMe Q optimal I/O size, showing that is 4K on a TLC drive and 64K on a Intel Solidigm P5316. Here's example Lua script for doing the storage is very straightforward. There were other things we looked at that involved more Ceph code changes. The beauty of our work is that the only Ceph changes we did was to enable Lua scripts to be able to write the storage class header, because most of the headers are they're read-only by default for Lua scripting. The RGW folks wanted to start off safe and only enable rewriting them as they saw purpose. So that's really all we had to do to Ceph itself. It was a very small change to Ceph. And the Lua lets us do all the flexibility without having to mess with Ceph itself, which means, fewer things you touch, fewer things you break, and, you can change it a lot more readily than, trying to, recompile your own Ceph. Replication and allocation with Lua. You can put 4K objects and 64K objects into the cluster without the users having to worry about the storage class headers. I should put class in there in this slide. And so the Lua script checks the object size and routes it to the proper pool based on the criteria that you give it. And so there's an example here showing the direction of objects and the space amplification for different object sizes. And here are some references. An Intel white paper, QLC cost-effective Ceph on NVMe, the 3 PRs that went into Quincy to affect this, general about Lua scripting, our email addresses, and I cannot hype Mark Nelson's. It's fantastic, dude. Trying to explain, the space amplification min allocation to people in words, it's hard to get across. And I came across his sheet, which has graphs that show you, visually, the space amplification for small. It's just so fantastic. And then a link to SNIA's TCO calculator, which is also the best TCO calculator I've ever seen, because it counts OpEx, it counts how much is your power cost, how much does it cost you to send somebody in to replace a drive. One of the things when you're planning out storage is, do you have to provision more drives than you need the capacity for just to get enough IOPS, which I have experienced when using SATA SSDs. Had to expand RBD clusters before the space was used because we needed more IOPS. There's a multiplier in there for that, so that, whatever media you want to use, all of the figures are in there so you can make informed decisions. And I think that's the last slide. This was originally written for last year's Cephalicon, which was going to be 4 miles from my house. I could have walked there, but it was a short enough flight here. Any questions? Anybody interested in using it, please contact me. I'd love to hear about it. Okay. Thank you.